in the fascinating world of chemistry. We're looking at change of concentration with respect to time. We're looking in terms of first order and second order. Now, this would have been incredibly easier last year if we had actually had nuclear chemistry, but we didn't get to it. So we'll do the best we can with this. All right. So first type of order reaction is called a first order reaction. This is referred to as a nuclear decay. This is we have, and the way we find this, we take the natural log of A to T, where AT is the amount that we have at a given time. AO is given the amount we have originally. Time is equal to a negative K, which is our constant, our rate constant, and our T, which is time. And we can either find that, and we use this one if we're looking, we use the first equation if we're looking for either K or T. Now, if I'm looking for either AT or AO, let me make this a little more clear because there we go. If I'm looking for either AT or AO, I use this equation. So it depends on what we're looking for. Looking K or T, we use the first equation. Looking A sub T or A sub O, we use the second equation. And my constant is 0.693 over T1/2. I'll show you in class how we get that value. T1/2 is what's called the half-life. All right, it's the amount of time that for 1/2 of the substance to react, or in most cases to decay. All right, so let's look at a problem. Determine the concentration of iodine that remains after 1.224 hours for the first order reaction if you initially have 2.250 molar and the half-life of the reaction is 14.56 minutes. All right, so we use the first one since we're trying to find the amount that remains, A sub T. We don't know it. AO is 2.250 molar. My K is 0.693 over T1/2, and for my problem, that's 14.56 minutes. We solve that through, we get 0.04760 per minute, and T is 1.224 hours. But if you look at it, my hours aren't going to match up with minutes, so I got to convert them, and 60 minutes is 1 hour, so I get 473.44 minutes. All right, so let's take our equation and plug our value in, and E. Now, when you do this, the easiest way to take care of this is where E is. Do that function first. So we're going to multiply negative 0.04760 times 73.44 and raise that to the E power. That's a function in your calculator. And we get 0.30326177. Now, I normally wouldn't write that down. I just keep it in the calculator, but I want to make sure that you see that you have the right number. And we multiply that by 2.250 molar. And we get a concentration at the end of 0.06823 molar. That's my answer. All right. Now, this one we'll also do in class. All right. Second order reaction. All right. It's slightly different. 1 over A to the T is equal to KT plus 1 over A to the O. And K is equal to 1 over T1/2 times A to the O. We don't have to have seconds equations. We can solve it through either way. So, determine the half-life of a substance with a second-order reaction. If after 31.223 minutes, the sample goes from 4.0987 molar to 1.09397 molar. All right. Using our equation, A to T is 1.09397 molar because it's at the end. AO, how much we started with, 4.0987 molar. K, we don't know because we're looking for half-life, and that's involved with half-life. And T at time is 31.223 minutes. So we have to rearrange the solve for K. So that's going to be 1 over A to the T minus 1 over A to the O all over T. Put those values in, divide through, and we get K is equal to 0.021472 per molar minute. We then have to solve for K for T1/2, so we have K. Just flip them around to get T1/2, put our values in, and our answer is 11.363 minutes. That's my answer. All right, this one we'll also do in class, and we'll do these as well. Any questions, let me know. Take care. Be good.